Alex, today we're still on the 2022 Columbia University Integration B qualifying round, and we move forward to part 2 that involves solving problem 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So before we jump onto the solution bit of this video, I'd like to encourage those of you who are here for the first time or are coming back but haven't subscribed to, please consider subscribing to our channel. Your support will really go a long way in increasing our profile and giving us that extra visibility that we need. So if you do like what we're doing, please leave a like. And if you know somebody that may benefit from this, please do share. So without much ado, let's go on and begin solving these problems. Problem number 11 is the indefinite integral of 1 over e to the power 2x plus 1. So the first thing we'll do here is just go ahead and divide both the numerator and the denominator by e to the 2x. So we have 1 divided by e to the 2x, and then e to the 2x plus 1 divided by e to the 2x. So what comes out of this is we have e to the minus 2x in the numerator over 1 plus e to the negative 2x. Okay, so we can then go ahead and re-express the numerator as negative a half times the derivative of 1 minus e to the negative 2x over 1 plus e to the power negative 2x. Now, it's important to know that if you have an integral where the integrand's numerator is the derivative of the denominator, that's the same as the natural logarithm of fx, of the denominator plus c. So with that in mind, our answer becomes negative half natural logarithm of 1 plus e to the power negative 2x plus c, or is equals to negative a half natural logarithm of e to the 2x plus 1 over e to the 2x plus c. So in summary, what we're saying here is that our integral of 1 over e to the 2x plus 1 is negative a half natural logarithm of 1 plus e to the negative 2x plus c, or negative log e to the 2x in the denominator, e to the 2x plus 1 in the numerator. And that, ladies and gentlemen, is our answer. Problem number 12 happens to be the indefinite integral of natural logarithm of x squared. Now, the important thing to note here is ln, which happens to be log to the base e of x, in our instance would also be equal to that. So let's just have that in mind. So this problem can be expressed as open big brackets log of x squared, so that we can say let u be equal to log of x. And that means that du dx is equals to 1 over x, implying that x du is equals to dx, and from here e to the u is equals to x. So using that, it means that this x is e to the u, du is equals to dx. So we're going to use that substitution, right? Such that the problem that is as follows in the x domain is the same as u squared e to the u du. Now, integrating this, I could also re-express this as that, and then we're going to use integration by parts. And what does integration by parts say? Integration by parts says that if you have an integral of a product of a function v and the derivative of a function u, that's the same as when you integrate that, it's uv minus u, the integral of u, times the derivative of function v. Okay, so if this is our u, then our uv is going to be u squared e to the u minus the integral of u, which is e to the u, times the derivative of u squared with respect to u. So we've come to u squared e to the u minus eu times the derivative of u squared, which is the same as u squared e to the u minus 2 u e to the u. Then we can re-express this apologies, we can express this as u times the derivative of e to the u. And so we have u squared e to the u minus 2, open brackets, u e to the u minus e to the u times the derivative of u, right? So this becomes u squared e to the u minus 2u e to the u plus this and this interacting e to the u du, because this now goes to 1. So this becomes u squared e to the u minus 2, there's a 2 here we had forgotten, eu e to the u plus 2 e to the u plus c. The integral of e to the u in the u domain is going to be e to the u. But we'd say that u is equals to the natural logarithm of x, right? So with that in mind, if our integral of u squared eu du is equals to u squared e to the u minus 2 u eu plus 2 eu plus c, then it means that squared, that's our original integral, is let's use eu first. This is x. U squared is going to be natural logarithm squared of x minus 2x natural logarithm of x plus 2x plus c. Now this is also equivalent to x log squared x minus 2x log x plus 2x plus c. So that, ladies and gentlemen, is our answer. Problem number 13, the indefinite integral of 1 over x minus x to the power 2/3. So one thing we could do with this problem is we could pull out x to the power 2/3 as follows. So we have 1 over, so remain with x to the 3rd here, left with 1 here, and that is dx over x to the 2/3. Okay, so we could try to substitute for that. So what I could say is let u be equal to x to 3. That means that du dx is equals to a third x to the power 2 over 3, which also means that 3 du can be used to substitute for dx over x to the power 2 thirds. So as we can see, this part here is awfully similar to that, and so we have 1 over u minus 1, and so 1 over u minus 1 means that the answer here is 3 natural logarithm of u minus 1 plus c. This u here, say u was set to be equal to x over third. Knowing that means that our answer to the integral of 1 over x minus x to the power 2 over 3 is 3 log of x a third minus 1 plus the integration constant. And that is the answer. Problem 14 happens to be indefinite integral of sine of x over square root of 1 plus cosine squared of x. So this is a very interesting problem. There are two ways one could approach it, but let's begin with the first method and just look at the elements of it. Okay. Now, we could, since if you look at this cosine x, there's a sine x here, would want to substitute for that cosine x there, and because whatever is in the numerator kind of beautifully allows you to do that, we just say let cosine of x be equal to, or let u be equal to that, and that means that du dx equals to negative sine of x, right? Meaning that we can substitute for sine x dx with negative du, right? So our problem here becomes negative 1 over square root of 1 plus u squared. Okay, and so one thing we could do, we have two options, and that's where this number one method, we could begin by saying let u be equal to sinh of y, or hyperbolic sine of y, and so du dy is equals to cos y, meaning that we could now substitute for cos y dy, du with cos y dy. Okay, so what that means is that if we have du over square root of 1 plus u squared, and there's a negative here, this becomes negative of cos y dy over square root of 1 plus sinh squared y, which becomes cos y, and the denominator here is cos y squared square root, which is cos y, and so as you can see, this is that, and which is negative y plus c. But we'd say that y is equals to, or rather u was equal to sinh of y, meaning that y is equals to the hyperarc sinh of u, right? And so in other words, negative du squared 1 plus u squared is equals to negative arcsinch of u plus c, but also u was set to cosine of x, right? So in other words, our original integral of sine of x over square root of 1 plus cosine squared x is the same as negative arcsinch of cosine of x plus c. So that was method 1. Now let's go to method 2 on just solving this problem 14. Okay, so these we were able to previously bring it up to a point where we had negative 1 over square root of 1 plus u, right? And so if we say let u be equal to tangent of x, not x, let's say theta, which is apt du d theta is equals to sec square theta, meaning that we can substitute for du with sec square theta d theta. Okay, and what does that mean? It means that our problem here that is the same as negative sec square theta d theta over 1 plus tangent square theta, which is equal to, so we have come to that point, the same as square root of sec square theta, which is negative sec theta. So solving that means that we have natural logarithm of sec theta plus tan theta plus c, but we had said that u was equal to tan theta, meaning that our problem that was negative du over square root of 1 plus u squared is the same as negative natural log of sec theta here is the square root of 1 plus tan squared theta, so this is 1 u squared plus u plus c, but we want to take this back to the original form. So in other words, sine x over 1 plus cosine squared x is equals to negative log of 1 plus cosine x plus cosine of x plus c, or negative log 1 plus cosine squared x plus cosine of x plus c. And I mean, I would leave you to prove that this is the same as, okay, I would leave you to prove it. Maybe, yeah, let's show that. Let's show that this is the same as this guy here. For those who may be interested, look, assume that u is equals to arcsine of cosine of x, such that sinh u is equals to cosine of x, and sinh u is the same as e to the u minus e to the negative u over 2, which is cosine of x, meaning that e to the u minus e to the negative u is equals to twice cosine of x, meaning that e to squared minus 1, if we multiply across by e to the u, is equals to 2 e to the u cosine of x. And so e to the 2u minus 2 e to the u cosine of x minus 1 equals to 0. And so if we have e to the u squared minus 2 cosine x times e to the u minus 1 is equals to 0, it means that e to the u is equals to 2 cosine of x, right, plus minus, using the quadratic formula, we have 4 cosine squared x plus 4 over 2, which is equals to 2 cosine of x. Pull the 4 out, we have 2 cosine squared x plus 1 divided by 2, which cancels. But since we know e to the 2u will always be positive, so we are going to remove. The only valid answer is going to be that. Okay. And so, in other words, u is equals to natural logarithm of cosine of x plus the square root of cosine of x plus 1. Okay, and so this proves for us that cosine of x is equivalent to square root of 1 plus cosine square of x plus cosine of x, or sinh of a function x, arcsine of that is the same as log of 1 plus x squared plus x. So this is something to glean from that. Anyway, without much ado, let's move to the next problem. Number 15, which happens to be the indefinite integral of 1 over x cubed times the square root of x squared plus 1. There are probably other methods. The one that quickly came to my mind is by substituting for x with tan theta. So just say let x be equal to tangent of theta, and that means that the x d theta is equals to sec square theta, implying that dx can be substituted by that. So in other words, in the x domain we have that, right? And in the theta domain we have over tan cube theta square root of tan square theta plus 1, which is the same as sec square theta d theta. This part here is sec square theta, square root is sec theta, so we have that, which means that we have sec theta d theta over tan cube theta. Okay, so what do we do next? So if we have come to a point where we have integral of sec theta over tan cube theta, that means that we have cos cube theta over sine cube theta times 1 over cos theta, which means that we have cos squared theta times 1 over sine cube theta, which is the same as cot squared theta times cosec theta. Okay. So what we do after that, I would like to, so we've come to a point where we have cot squared theta, cosec theta integrated, which is the same as the integral of cot theta times the derivative of negative of cosec. It's not cos. Cosec theta. And so using integration by parts, where if we have v du integrated, we have uv minus u dv. Using this, our problem now becomes a negative cotangent of theta, cosec of theta, plus cosec theta times the derivative of cotangent of theta. Okay, so which means that we do have now cotangent of theta, cosec of theta, plus cosec of theta times negative cosec squared of theta. Okay, so that means that we do have negative cotangent of theta, cosec of theta minus cosec cube theta. And we could re-express things a little bit differently. So we have cosec squared theta, cosec theta, and this part here is the same as cotangent squared theta plus 1, this part here. So what that means is we have cotangent of theta, cosec theta, minus integral of cotangent squared theta plus 1 cosec theta, which means that we do have cotangent of theta, cosec of theta, and so we have cot squared theta, cosec theta, plus cosec theta is theta. Okay, so we've come to where we have now cotangent of theta, cosec of theta minus cot squared theta, cosec theta minus cosec of theta. Now this is where we started, so this is I. In other words, we can pull out, and so we have 2I is equals to cotangent of theta, cosec of theta, minus cosec of theta integrated. This is an interesting bit, so let's focus on this for now. What is cosec? Cosec of theta. Cosec of theta is the same as 1 over sine of theta integrated, and if we say let t be equal to tangent theta over 2, using that, that means that dt d theta is equals to a half sec squared theta over 2, which means that 2 dt over sec over 2 is equals to d theta, and so this is the same as 1 plus tan square theta over 2. This becomes 1 plus t squared is equals to d theta. Okay, so that being the case, and we know that if we have our triangle and this is theta over 2 and t is tangent t is tangent theta over 2, which is opposite over adjacent. So this is how our triangle is going to be, so that sine theta, which is 2 sine theta over 2 cosine theta over 2, is going to be equal to 2t over that, which is t over 1 times 1 over that, which is square root of 1. That which becomes 2t over 1 plus t squared, right? So that the integral 1 over sine theta is equals to 1 over 2t over 1 plus t squared, 2 dt over 1 plus t squared, and so this and that cancel, and this and that cancel. We have an integral of 1 over t, which is log of t plus c, which is log of tangent theta over 2 plus c. Now, our original problem, we said 2I is equals to negative cotangent of theta cosec of theta minus the integral of cosec theta, right? This now means that I is equals to negative a half cotangent of theta cosec of theta minus a half cosec of theta. And so we could re-express this into 1 over tangent of theta. One important thing to note here is that this is the same as 1 over sine theta minus, we've already ascertained that this is the same as log tan theta over 2, and we have integration constant c there, so that if we have this as theta, and initially we had expressed x to be that, then it means x over 1 is that, and the hypotenuse becomes that. And so our original problem, which is 1 over x cubed square root of x squared plus 1 is equals to negative 1 over x. Sine theta here is the same as this over this, but inverse, so we get 1 plus x squared over x minus half log of, so we're going to have to invoke a half angle situation here. So what is tangent theta over 2? So if tan theta is the same as twice tan theta over 2 over 1 minus tan square theta over 2, what does that mean? It means that x is equals to 2 tan theta over 2 over 1 minus tan square theta over 2, and therefore x minus x tan square theta over 2 is equals to 2 tan theta over 2, meaning that x, if we add both sides with this, we have that plus 2 tan theta over 2 minus x equals to 0 using the quadratic formula means that tan theta over 2 is negative 2 plus minus square root of 4 plus 4x squared over 2, which means that we have 2 plus minus, pulling 2 out, we have 1 plus x squared over 2, and this would cancel, meaning we found that tan theta over 2 is equals to negative 1 plus minus square root of 1 plus x squared. If we choose the negative, that means this will perpetually be negative, so the only reasonable thing for us is to go with that. And so our problem was 1 over x cubed square root of 1 plus x squared. This was equal to negative a half square root of 1 plus x squared over x squared minus a half log of negative 1 plus square root of 1 plus x squared plus c. And that is our answer. Problem number 16 happens to be the indefinite integral of sine of 6x times cosine of x. Now, we all know that sine of a plus b is equals to sine of a cosine of b plus sine of b cosine of a. Sine of a minus b is equals to sine of a cosine of b minus sine of b cosine of a. So that when we add this, we have the fact that sine of a plus b is sine of a plus b plus sine of a minus b is equals to 2 sine a cosine b, right? And so sine a cosine of b is equals to a half sine of a plus b plus sine of a minus b, right? So with that in mind, if a is 6x and b is x, we can get that our problem sine of 6x cosine of x is equals to a half sine of a plus b, which is 7x, sine of a minus b, which is 5x. So which becomes a half negative 1 over 7 cosine of 7x minus negative 1 over 5 cosine of 5x plus c. And so just to summarize it, we have sine of 6x cosine of x is equals to a half negative 1 over 7 cosine of 7x minus 1 over 5 cosine of 5x plus c. And that, ladies and gentlemen, is our answer. Number 17 happens to be the indefinite integral of tan squared x times the second squared of x. Okay, second to the power 4 of x. So we can re-express this as tan squared of x times sec squared of x times second squared of x. And since we know that sec squared of x is same as tan squared of x plus 1, we get tan squared of x sec squared of x plus sorry, this is tan to the 4th of x times tan squared of x sec squared of x. And since this is the same as squared is the same as tan of x. This is the same as tan of x. This means that we just this is what we're doing here. Right? So we integrate the derivatives of those functions, we come to a fifth tan to the power 5x plus a third tan to the 3x plus c. Therefore, the integral of tan squared of x times sec fourth of x is equals to a fifth tan to the power of x plus a third plus c. And that there is an answer. Number 18 happens to be the indefinite integral of 1 plus x over 1 plus x squared, which we can just re-express as we just separate this into two. Right? And this is the same as 1 plus 1 x squared integrated plus a half the derivative of 1 plus x squared over 1 plus x squared. So this is a famous integral, so this is the arctangent of x plus a half the natural logarithm of 1 plus x squared plus the integration constant. When you're integrating a fraction whose numerator is the derivative of the denominator, we're going to have a natural logarithm of the denominator. So in other words, 1 plus x over 1 plus x squared is equals to the arctangent of x plus a half natural logarithm of 1 plus x squared plus the integration constant. And that is the answer. So on to problem number 19, and that is the indefinite integral of 1 over x plus 1 plus x square root of x cube. So my first intuition here is to just substitute for the square root of x, and we'll just say let u be equals to square root of x, meaning that u squared is equals to x, and so d2 u du dx is equals to 1, meaning that we can substitute for dx with 2u du. Okay, so in other words, our problem that is in the x domain here becomes okay, and we could also say let y be equal to 1 plus u such that dy du is equals to 1, meaning that we can substitute for du with dy, so that our problem that is becomes 2. From here we see that y minus 1 is u over y cube, which becomes 2 1 over y squared minus 1 over y cube. Okay, so the fact that our problem now becomes 2 1 over y squared 1 over y cube is equals to now 2 in bracket negative 1 over y plus 1 over 2y squared plus c, but y is equals to u plus 1. That in mind, our problem that is 2 u over u plus 1 cube becomes 2 negative 2 u plus 1 plus this and that cancel, so we have 1 u plus 1 squared plus c, but also since we said u equals to square root of x, that means that our original problem, that is 1 over 1 plus is equals to negative 2 1 plus square root of x plus 1 over and that's the answer. To problem number 20, which is the indefinite integral of 1 over the square root of tangent of x. One thing we could do is we could let just let u be equal to the square root of tangent of x, which means that u squared is equals to tangent of x, implying that 2u du dx is equals to sec of x, and so is equals to sec squared x equals to that, but also this is the same as right. From here we see that u to the fourth is equals to, right? So in other words, 2u 1 plus u to the fourth okay, so that when we have this, and since this is being equated to u, we have 1 over u, and plus of dx we have 2u du over 1 plus u to the fourth. Okay, and so our problem becomes 1 over 1 plus u to the fourth integrated. This is interesting, right? Because if we have 1 plus u squared and we square that, this becomes 1 plus 2u squared plus u to the fourth. And then 1 plus u squared minus 2u squared is equals to 1 plus u to the fourth, right? Because I do really want to express this as a partial fraction. Now using a difference of two squares, because if you have something like that, we have a plus b, a minus b, right? And this here is the same as 1 plus u squared minus square root of 2u squared, right? This becomes 1 plus u squared plus root 2u, 1 plus u squared minus root 2u. In other words, our integral 1 over 1 plus u to the fourth is the same as 1 over 1 plus u squared plus root 2u, 1 plus u squared minus that. And so the next thing is, how do we express these into a partial fraction? So we could just say this is the same as au plus b over 1 plus root 2 u plus u squared plus cu plus d 1 minus Okay, so that 1 is equivalent to AU plus B, 1 minus root 2U plus U squared plus CU plus D, 1 plus root 2U plus U squared. And so this can be expressed as so A plus C U cube, and then we have plus negative root 2A plus B plus root 2C plus D U squared plus A minus root 2B plus C plus root 2D U plus B plus D. Now the U terms here, we see the constants will be equal to 0, but this will be equal to 1. So what we have here is essentially B plus D is equals to 1, and then A plus C is equals to 0 from here, and then what we have next, negative root 2A plus B plus root 2C plus D is equals to 0, and finally A plus C plus root 2, pull that out, and then we have negative B plus D is equals to 0. So this and that equals to 1 from this, and from here we have A is equals to negative C. So what do we know? We know that A is equals to negative C. We also know that root 2 in bracket negative A plus C equals to negative 1, and since A is equals to negative C, we see that from here we'll see that 2 root 2 negative A is equals to negative 1, and therefore A is equals to 1 over 2 root 2, and C would be equal to negative 1 over 2 root 2, and since B is equals to negative, I think B would be equal to, let's wait a minute there, because we had ascertained that A plus C plus root 2 negative B plus D would be equal to 0, and since this also goes to 0, then it means negative B plus D would be equal to 0, meaning that B is equals to D. One crucial thing to note for us is that B plus D is equals to 1, so that means that B is equals to a half and D is equals to a half. Okay, so in other words, since we have 1 over square root 1 plus root 2U plus U squared, 1 minus root 2U plus U squared being equal to AU plus B over 1 plus root 2 plus U squared, root 2U plus CU plus D over 1 minus root 2U plus U squared. This is the same as 1 over 2 root 2U plus a half over 1 plus root 2U plus U squared, plus negative 1 over 2 root 2U plus a half over 1 minus root 2U plus U squared. And we can keep on going. One thing we could do is we could pull could say this is the same as 1 over 4 root 2, so that we have 2u plus 2 root 2 over 1 plus root 2 plus u squared minus 2u minus root 2 twice of that, 1 minus root 2u plus u squared. And this becomes 1 over 4 root 2. We have 2u plus root 2 over 1 plus root 2u plus u squared minus 2u minus root 2 over 1 minus root 2u plus u squared plus, because there is an extra one here, root 2 over 1 plus root 2u plus u squared plus root 2 over 1 minus root 2u plus u squared. So that is going to be our partial fraction, and we'll continue from there. So our integrand, 1 over 1 plus u to the 4th, was the same as 1 plus root 2u plus u squared, 1 minus root 2u plus u squared, plus 1, which we found to be that 2u plus root 2 over 1 plus root 2u plus u squared minus 2u minus root 2 over 1 minus root 2u plus u squared plus root 2 over 1 plus root 2u plus u squared plus root 2 over 1 minus root 2u plus u squared. Therefore, the integrand of 1 plus 1 over 1 plus u to the 4th is the same as 1 over 4 root 2 that plus root 2 over 1 plus root 2u plus u squared plus root 2 over 1 minus root 2u plus u squared, which is the same as the derivative of 1 plus root 2u plus u squared over 1 plus root 2u plus u squared minus the derivative of 1 minus root 2u plus u squared over 1 minus root 2u plus u squared plus root 2 over u plus root 2 over 2 squared minus a half plus 1 plus root 2 over u minus root 2 over 2 minus a half plus 1. Okay, so here we get the natural logarithm of 1 plus root 2 u plus u squared minus 1 over 4 root 2 natural logarithm of 1 minus root 2u plus u squared. And then here we are still left with an integral of root 2 over u plus root 2 squared plus a half plus root 2 over 1 u minus root 2 over 2 plus a half. Okay. The important thing to note here is we can equate this guy to root a half tan theta, and then integrate, So maybe, yeah, let's do that. Let's see how to solve these last parts. Okay, these two integrals. Okay. So we have integral of root 2 over u plus root 2 over 2 plus a half. This is squared. If we say let u plus root 2 over 2 equal to 1 over root 2 tan theta, that means that du d theta is equals to a half root 2 sec square theta, and so du can be substituted by that. And so our problem becomes root 2 a half root 2 sec square theta over tan square theta over that, actually squared, I apologize, so plus a half, which is equals to, now this half goes out and becomes 2, and this would cancel, so we have 2 sec square theta tan square theta plus 1 becomes sec square theta, and so we get 2 integral of 1, which is 2 theta. So let's just make sure we have everything teed up. Yeah. So we have root 2 here, and this guy here was moved in there, and we have a half tan square theta plus a half that goes up as 2. So in other words, we have 2 arctangent of, from here we have root 2 u plus 1 equals to tan theta, and therefore theta equals to arctangent of root 2u plus 1. So this becomes root 2u plus 1 plus c. How about for scenario, we say let u root 2 over 2 be equal to 1 over root 2 tan theta, so du would be equal to and so our problem becomes over a half is equals to 2 sec theta over sec is equals to 2 theta plus c, and from here we see that root 2 minus 1 equals to tan root 2u, and so theta is equals to arctangent of root 2u minus 1. So this becomes 2 arctangent of root 2u minus 1 plus c. So because our integral of 1 over u fourth had come to a quarter, log of 1 plus root 2u plus u squared minus a quarter root 2 log of 1 minus root 2u plus u squared and plus 1 over 4 root 2 u plus over that u minus 2. Okay, this becomes, we can consolidate the logs using the rules of logarithm. So we have 2u plus u squared over 1 minus root 2u u squared plus 1 over root 2. We find this to be 2 arctangent of root 2u plus 1 plus 1 over arctangent of root 2u minus 1 plus c. So this was twice. So 2, and so 1 plus root 2u plus u squared over 1 minus root 2u plus u squared plus 1 over 2 root 2 arctangent of root 2u plus 1 plus root 2u minus 1 plus c. But we had said u was equal to the not theta but x rather, and also our integral is 2. So this becomes twice c, and so which becomes 2. Actually, let's get rid of that 2 by multiplying it across and then substituting this to be u. So we have 1 over 2 root 2 natural logarithm of 1 plus 2 tan x plus tan x plus tan x plus 1 plus c. And that, ladies and gentlemen, is our answer. Okay, I don't know if you do have any questions on one of the steps, or if we made a mistake. Anyway, we do we are open to your suggestions and corrections, and any form of input. So without much ado, until next time, thank you so much for staying put. Bye-bye.